In C++, there is a concept called design patterns. There are books being written. There are some very nice books actually being written on design patterns. There are uncountable number of design patterns out there, and many of them are not related to HPC at all. They're just some kind of idiomatic way of approaching some kind of problem. So if I have to visit a data structure which is using a lot of inheritance, I can use the visitor pattern to visit my data structure in a kind of standard way. But it's not really something you will find often in a HPC scenario. There are, and the problem with patterns is that, okay, they're just code, okay? They're just code, and there might be a few tricks that you might learn there, but it's just code. So we are going to show you in this course two main patterns that we think might be useful in your work. Of course, I don't know what your work is, so I cannot predict what patterns will be useful to you. But in our experience, the CRTP and the proxies are the most common patterns that we use in our real life, in our work. Let's go with the CRTP, curiously recurring template pattern. That is simply having a class that inherits from a base class which is templated with the type of the derived class. So technically, that's how it is. The class derived inherits from the base, which is a template class, which is instantiated with the type of the derived class. And derived 2 is the same, right? You derive from derived 2. In the object-oriented world, you will see that this base class will have a virtual method get, and then you get the derived, they get the get method, and the derived 2, they get the get method, and the runtime dispatch, the vtable lookup mechanism will go into the right implementation at runtime, performing basically a switch case statement, or something more efficient if the compiler can figure it out. In the case of the CRTP, this has to be explicit, so you have to do a static cast to the derived pointer of these, because the base class now is the base of the derived. So if I pass, if I want to call the actual implementation, I need to cast it to the derived pointer and call get, and this get will be called in the derived class. Advantage of this thing is that the name of this method doesn't have to be the same as the name of the base class. So I can call here, instead of get, calling, oh, this is my get implementation, and then I get my get implementation here, and I call that method there. But yeah, it's an advantage and a disadvantage at the same time. I think it's a good thing. But so the pros is that when you do this, you don't have vtable lookups anymore, because the static cast is resolved at compile time. The compiler knows how to cast it. The casting is simply changing the little table that refer to what data members, where data members are, what are the offsets of the data members, and that is basically done the compiler. It's a compiler that does it. There's no code that reflects that. So static cast is efficient. The problem with this thing is that now the derived and derived 1 do not derive from a common base. They derive from two different bases, two different types. So you cannot do really runtime polymorphism. So another problem with the CRTP pattern is the fact that if I access my derived, inside my base, if I access my derived class like accessing a type member, for instance, then I get the compiler error because it says, well, derived is an incomplete type. Because derived has been defined after. So derived is defined after the base, so it doesn't know what derived is when it instantiates the base. Quite annoying problem. So if you really have to do this, you have to use the traits classes. You have to use the trait classes to pass information about that derived class in some way, and using forward declaration. So you declare the trait classes with some template name, and then the base access the traits. Then you define the trait classes as a specialization for your derived type, and then you can access that thing. So I leave the code there. When you get the slides, you can study it. It's a little complicated. So in our library, in the library that we are developing, we are using the CRTP basically everywhere, not only because it gives you this polymorphism, but it really gives you the better functionality. It just works charmingly out of it. When you start thinking about it, just comes out, oh yeah, why not just template my base class and it work efficiently. But yeah, this might be a trick, but you find out how to fix it. It doesn't pollute the user experience if you do it nicely, right? The traits are basically library components, so that the user doesn't have to see this kind of stuff. So it becomes a library developer burden. So what about performance then? Why would you want to do this? Well, I don't know why there's this line here. This guy, hate it. Okay, so we have on the left side we have the old-fashioned object-oriented solution in which you have a virtual member function, which is process, which is abstract in the base class, is not specified. Then we have a derived I and derived C. It's called because the derived that computes on integers and the one that computes on complex numbers. And they define their own process, which is a virtual. Okay, it doesn't have to be, but it's virtual and in an object-oriented fashion. And when you pass this derived I, derived C to a function that requires that takes a base pointer, the right implementation will be selected at runtime, and you have the runtime dispatch. In the case of the CRTP pattern, the only difference is that, okay, you have to derive from a template, and the process method is no longer virtual, but is calling forward the call to the method of the derived class. Now I'm using different names here. Is a process underscore instead of process in the derived class, because it makes clearer sometimes the fact that this is just an implementation of that functionality. That is the message you want to convey. But you don't have to. It can be the same name. And so in this case, yeah, you call the process, which is not virtual, and you get this behavior. Now, if you call this from within a function that takes a base pointer or a base object, right? It takes a base pointer in this case, right? And you get runtime dispatch. Here you cannot take a base pointer only. It has to be a template. So whatever function that deals with this must be a template that receive a base t, where t is a template argument. So it will be compile time dispatched also. It will be instantiated at compile time. So what is the performance of this guy? What is this guy giving in terms of performance? So we have already built our CRTP, and we go and we do CRTP and CRTP. We pass. So this test runs that example that I show you in the slide, and runs this method, this overloaded method, a certain number of times, and a certain number of times has to be specified in the command line. Let's say 1 million. Maybe 1 million is too little. Yeah, let's put 10 million. Yeah, to get some decent time. Actually, let's go to 50 million. Okay. So now, if I'm looking here, I'm saying, okay, this is the runtime version. Okay, runtime version takes 335, and the compile time the same time, and what's going on, and so the runtime here is 28, and the compile time is actually slower. So something wrong here. What's happening? Well, I'm compiling without optimizations. So if I'm so basically without optimization, well, in this case, actually the compile time is even faster without wait a second. This is already the optimized one? Might be. Yes, this is the folder I wanted to go. Yeah. Okay. Okay. So without optimization, the compile time is actually slower than, or comparatively the same as the runtime dispatch. But now if I compile by end with optimizations on, I should get a better performance. I live my life on the edge. Oh, STD. Yeah, I never trusted default. I'm a computer scientist. Code and CRTP, CP. It's 8. Yeah, you're right. I wanted actually that to be this way. Yeah. 1, 2, 3, 1, 2, 3. So now the runtime dispatch is basically the same time, but the compile time version, which is here, is in the case of the integer computation is twice as fast. In the case of the complex, is basically the same. Where is it? Yeah, and the case, this is all runtime. Sorry, where is it? There's only must have commented out something. So the derived I is 0.28 and the compile time 0.15. So still not that faster, but well, it's almost twice as fast. In this case, in the case of complex, the speed up should be much bigger. Yes, in the case, so we have the runtime derived C, which is 0.14, and this one is 0.04, which is still 3 times actually less. Yeah, almost 3 times fast, more than twice as fast. So as you can see, I'm running twice this. I have to look at this code. I have to fix it. But anyway, when you compile with optimizations, you get better performance. Why is that? Because you, in the runtime polymorphism case, you just get the if to select which function to call, and you call it. In the compile time, if you don't optimize, you call the base one. The static cast might be also be doing something, probably not, and then you call the derived. So there are 2 function calls, at least, which makes the thing slightly slower. But when you optimize, the compiler inlines these intermediate calls, and you get better results. So you get better performance with the CRTP pattern. And as you can see, there's no overhead in terms of code. There's a little overhead in terms of code. And there is also an exercise for the CRTP that what allows you to do. For instance, it allows you to, if you want to collect statistics around time about the use of your classes, this is one of the exercises you will find in the folder. So use the CRTP pattern to collect statistics on the usage of your classes. Just one example, and it can be used in many different ways. Okay, so questions? As many of the things in C++, you might say, why the hell do I need this? When you start looking around, you will find it around. You will find the ways. The problem with these things is that you have to know that these things exist before you can think of using them, right? But when they pop, when you know they exist, then you start seeing them around. It's like extra paranormal things. Should we go into the coffee? Should we dive it there? Okay, so we go on with the patterns, and we finish this session with the proxy. Another pattern that is very common to produce APIs that are flexible and powerful. What is a proxy? A proxy is an object that behaves like some other object. And sometimes is adding behaviors, is adding functionalities and control, but it's basically a proxy, something that appears to be something else than what it is. So, for instance, this is useful if you have an object which is very heavy to copy, and you want to you have to use some by value function, and you pass a proxy to that object, which contains a reference to that guy, to the heavy guy. So you just copy you can copy the lightweight object. It is used also in some runtime systems, for instance, for parallel computing, in which you have an object in your address space, which is referring to an object which is sitting in some other node, and so in some other address space. And it has the same interface. It behaves like that, and it forwards the calls and the operations to the remote object. So you don't want to move objects very often, so you want to, for instance, coalesce a certain number of operations to be sent once instead of sending every time the message. So these runtime systems usually use this kind of functionality to hide from the user the fact that there's all this process going on. So the proxy is actually not the object, so it's something that behaves like an object. So it has some constraints sometimes. The fact that some constraints on the way you can copy or move these objects around. But we will see one example that I hope will make clear what a proxy really is. How proxy works and how they can help you. Like all the patterns, which are just code, so the boundary between a pattern and known pattern is not really clear. So a CRTP pattern in which you collect statistics on the use of your class is not technically strictly CRTP because you're doing something else, right? But it is basically working around the same concept. And proxy are pretty much like that. So if you add the functionality to an object, if you add possibility of control this object in a different way, the proxy is not really the same as the object which is proxying to, but it's still considered a proxy. So let's consider this example. We want to run a finite difference operation on certain number of data fields, multidimensional arrays, storages, whatever you want to call them. So we will have like a where is it? Okay. We will have like our fields or our data fields would be like three-dimensional arrays in this case. One is called the input, the other one is the output, and the sizes are n, m, and l. This is just a three-dimensional grid, for instance. And I want to do a Laplacian on this grid, and I can do, and I want to do this operation, right? I want to iterate over the points. And when I am at the point in this three-dimensional array, I want to access the neighbors and do some operation with the neighboring points and update my output value. This is a Jacobi iteration. I write into the output in the point of evaluation, and I access my input in the surrounding points, and I update my output. So I want this API to work. I basically say, I want to apply this lambda function. I don't want to create a specific struct or for loops. I don't want to see for loops. Typically, in highly abstracted code, you don't want to see the loops, okay? It's a kind of general idea that if you write the loop yourself, there's something wrong in your API. You should not write loops. You should write construct that implies some looping or some iteration, and then will be the compiler or the library or someone else to implement their loop efficiently for your architecture. So here, I don't want to write the loop because if I write the loop, I have to specify too much information. I specify the control flow of my code, and the compiler might not understand that it can do some optimization. So I want to leave that to the library. So try to avoid loops as much as you can in the user code. So now I want to have this lambda. I want this interface to work. So I want to get this P in and P out to get inside my lambda. And I want to access the neighbors in the iteration points in which I am. And I want to apply this lambda in all the points that matters to me. So for instance, then I have to specify, well, listen, since these I have like accessing neighboring, I cannot iterate over all my data structure, otherwise I go out of bound, right? I get 1 + 1 on the wrong side. So I would say, restrict my iteration space by 1 point in all 3 dimensions. So whenever I access, I will always be inside my storage. And I want to operate on the input, which will be the first argument passed in, the const ref, and the output, which be the reference. So it will be something that will change the content of the value that is referring to. So is this interface clear to everyone? Right? The idea now is that the library internals that provides this functionality will pass to this lambda something which is not a reference to a value or a pointer, will pass a proxy to a value of the storage. which act like storage references, but it can also add this added functionality to access the neighbors efficiently. So internally, the guy will call this, so the user will call stencil run with a lambda and the elo and the data fields. Internally, the library will have a for loop or a loop nest. Will create this proxy, passing them, and then call this lambda function that the user provides. So what is the proxy? The proxy, you can find it in the example folders for the proxy, into the proxy folder in your code. Well, the proxy, as the main component are, it has a reference to the storage is pointing to, and has a do I have it? Okay, so you have an access source to access the storage, which is the interface that we saw earlier, right? This guy, this P in 001, 0 minus 1, 0. This will be this function call operator with 3 integer parameters. You have 2 versions of it. One is const qualified for the read-only parameters. The other one is not const qualified to return a reference to a value, to actual double just stored in the storage. And the accessor will access this storage pointer, the pointer of the element we just pointed to, plus an offset, which is computed given the indices. Another point that I didn't stress in this slide is the fact that I have here a row pointer to something in the storage. Why is it it is a row pointer? Well, it is acceptable to use row pointers sometimes when the row pointers are not owning the resource. So I'm just using a pointer. The pointer is not owning anything. I'm not doing a new statement on that row pointer. I'm just pointing to an element inside the storage. And I need the flexibility to increase pointers and do pointer arithmetic in a very natural way and in a very confined space. So a row pointer here, I think, is acceptable. We need some additional functionality to use on the library to position the proxy to a particular point in the storage. So for instance, we set the pointer to the storage, and the storage, assuming have this IJK functionality to access a value, right? It's just a storage type. And you get the address of it, and then you get the set the pointer. You construct like this. You construct with the reference to the storage, and you set the pointer to null pointer. And then also have an increment function that does the plus plus pointer. So when I move to the next iteration point, I go through the iteration space according to the data layout, so I can increase the pointer instead of recomputing the offsets, even though compilers are smart enough usually to figure out that it's just an increment. But just to be on the safe side, I will just say increment the pointer. You don't need to do any arithmetic operation when you move from one iteration point to the next. So this is the proxy. How does it work? The stencil run implementation, which is the function that the user call, takes the stencil operator, say the definite difference operator, which is the lambda. Here it takes it by value. It's probably not a good idea. You can take it like R value reference or applying the forwarding. It takes the elo type. Now the elo type is just an argument here. It doesn't need to be named. It doesn't need a name. So when I'm passing this guy, I don't have the corresponding variable in the function. So you know, I guess everyone knows here that if I pass just the type here and not the variable name here, this is still a valid signature, only that the variable would not be accessible inside the function. But I don't need the elo variable. I just need this type to understand what are the I, j, and k values. As you can see here, I constructed the elo type in this line, and these values are compiled time template values that I use later on. So this is a specialization which I take I, j, and k as a template arguments, and I expect some elo type with some I, j, and k values. So then I can access I, j, and k in my code. And then I have a pack of arguments which are the storage types that I want to work on. And this is a storage type. This is an expansion pack, so the number of arguments there must be the same number of arguments that the lambda of the finite difference operator accepts, so I can pass them to the finite difference operator. If it's not, it will give me a compiler error, and I can actually check that at compile time. And then in this simple experiment, I will just have 3 loops that goes from the elo to the elo size to the size minus the elo size, and then move the proxies to some point. And then I will call my operator with my argument packs. This requires to transform a tuple. I have to create the proxies. So I take my storages and I create the proxies. For each proxy, I create a proxy. For each storage, I create a proxy using the pattern expansion that we saw before. This will become proxy data 0, comma, proxy data 1, etc. And we'll make a tuple out of it. Now I need to take a tuple and transform it into a pack expansion again. And this is a trick that we will see later, actually. You're showing that, right? Paolo will show you how this trick is done. It's not that intuitive. You need to use this make integer sequence. But basically what it does, it takes this proxy, unpack them, and call the function, and we'll call the function, the operator, with these proxies, and then we'll increment the pointers on the proxies. So I have some helper functions around that will do this increment. This is just an implementation that works, for instance, in the single-threaded environment, in which my layout has a stride 1 on k. So I increment the pointer, and I will have an efficient iteration on my data. If I want to run on a multi-threaded, I just change the loop structure here. I put open and p threads wherever I want. If I want to work on GPUs, this guy might be just a GPU kernel. And the user API will be exactly the same. The user will always say, I want to apply this lambda in these cases. Now, with the GPU probably doesn't work well because the lambdas are not very well handled at the moment, especially the C++14 lambdas, but they will come. Someday they will run. Call is just, I'll show you. So this is a storage type. Can everyone see nicely? So the storage type is just, it has the constructor and it can access the data given the offset, and it has some function to access the sizes, very simple. The yellow type is simply just a template class with no data members, no member functions that just have these context for values that I don't even need. So I don't even need that one. It can be just an empty class with a template argument for how I'm using it. And now there's a namespace detail here in the real code in which I have the call operator and I have the proxy. So the proxy is exactly the code that we showed before, a couple of methods more, basically shortcuts if I want to be, if I don't want to write 000 every time, I can just do open and close parentheses and mean the same thing. And the call is simply this guy here. So the call takes an operator, so the stencil operator or the finite difference operator, takes the proxies, which is the, is like the, I think it's a tuple of the proxies. Yeah, it's a tuple of proxies, plus this integer sequence that is the streak to access these guys, okay, to transform a tuple into a pack. And here it is. You go to you get a tuple. So this is a tuple of proxies, and you want to get the you want to call the operator with the first proxy, the second proxy, the third proxy. And so you do pack expansion on this integer sequence, which is just a type, and you do pattern expansion here. So this will become std integer sequence is just a sequence of integer from 0 to the max, so 0, 1, 2, 3, 4, right? If it is 5 elements. So it will become get 0 from the proxy, get 1 from the proxy, comma, get 2 from the proxy, get 3 from the proxy, and you just call the lambda function with that guy in there. So this is just a trick, because the C++ doesn't allow you easily to transform tuples into packs, so you have to create an intermediate step to do it. Performance-wise, you should really not be concerned. These things are very well inlined usually. So the call is this trick. And I need to call, in my code, I need to call this guy. So here okay, this is the recursion to update the pointers. So other few helper functions, and this is the code that we saw in the slide. To test this thing, I realized I wanted to run the test to do this, right? So let's go. And I go here and I say, okay, I want to run my stencil run with my Laplacian operator, my elo and stuff. I write it, I go. And I soon realize, well, but even initializing the data, it's basically an iteration over the points. So why don't use the same stencil run to initialize the data and to print the data out? It becomes a little tricky because you have to do a lambda with captures and of references, integers. But you basically can do stencil run. Now you want to iterate over all the points. So elo type is 0, 0, 0. So you want to iterate to all the space. And you initialize out to 0 and in to I plus j plus k. Then you update I, j, and k, which are references. Then you do SDC out, and you want to print it in a very nice way, like in a 3D fashion. Then you run your stencil, and here I have then I print the output. A second. And then here I have a test that checks that the result is what I expected, that runs the Laplacian as you would write it in a typical for loop nest. I could have run these also using the stencil run, but this would have been kind of cheating. I cannot test my code using my own code. That will be like if I make the error that make the test pass, I will never find out. So I write this one as a different functionality at a lower level to check that the results is correct. Now, before going to the questions, just to make, if I make we construct the stencil, we go into the proxy and run the stencil, and I guess the size has to be specified here, I'm not sure. And here you have the output. This is the input. Now you compute the output, and you see, and then you have the check that says the test passed. There was a question on the back?
If you go back to the init thing, can you explain the last two lines, the k, if, the two ifs?
What, here? No.
Yeah, inside this one you have if.
Ah, yeah. Oh, that is just a trick to go on a new line. I want to do, so the trick is like this. It's really a dirty trick. I don't think you can do any better, by the way, but I think that I declare these size t, these integers, initialized to 0 outside my lambda. Then I capture those by reference here, and I also capture by value the size of my storages. Okay? So by value, I capture n, m, and l, and by reference, I, j, and k. Now I write output, I set to 0, in, I set to I plus j plus k, and then I increment k, and then when k gets to the end of my third dimension, I set k to 0, and I increment j. When j goes to the other thing, I reset j, and I increment I. So I will have all the I, j, k. I will iterate through the iteration space. This is a trick because this assumes that the loop inside is for I, for j, for k. If I implement it for a GPU or for some other multi-threading scheme, this will not work. Okay. But this is really like a simple toy example of what the stencil thing will look like. And I don't want to go into there. This is my daily job to do API for stencils. So that it is just a toy example, but just to show that using this proxy concept, we can really write, I think, a natural interface for specifying stencil operations. And if you want to be more sophisticated, then you need more sophisticated implementations, definitely. Definitely. Other questions? Do you find this interesting? Who finds this interesting? Who doesn't find this interesting? Okay. Good. So let's move on to the next topic, which is const expert. Back to the hardcore C++ features.